Hey, Honors Kim. Today we are going to be talking about some of the trends that the periodic table tells us about atoms. So from the periodic table, we can learn a lot about elements. We've talked about kind of the different categories that they're in, metal, non-metal, metalloid. We've also talked about the families that they could be found in, but we're going to be hitting now on some of the trends that the overall periodic table tells us. So based a lot and pretty heavily on the attraction of positive charges to negative charges. So I told you guys at one point that in chemistry, almost everything is governed by positive and negative things being attracted to each other, and this is no different. So for review, we know that the nucleus of an atom is made up of protons and neutrons, so the nucleus is going to be positively charged. The negative electrons are going to be therefore attracted to the nucleus. So what we see is that there is a bit of attraction of every electron to its nucleus. So when we're looking at an atom like this, the nucleus being positively charged, the electrons are going to be attracted to it. That's what keeps them attached to the actual atom itself. So otherwise, they would just kind of fly off into space. Now, what keeps them from going all the way in is their energy, their momentum, and their centripetal force that keeps them kind of on their pathways through the orbitals. But if the attraction of the nucleus, because it's positive, to the electrons is because they're negative, then the more positive the nucleus gets, the more we're going to see that attractive force. So the more protons you have in a nucleus, the greater the nuclear charge is going to be. So that's our first parent trend, is nuclear charge, the charge of the nucleus. Now, every nucleus is going to be positively charged, but the more protons you have in your nucleus, aka the bigger your nucleus is, the more positively charged it's going to be, so the stronger the force is going to be on its electrons. Now, the other major parent trend that kind of fights with nuclear charge is shielding. So with shielding, what we have is, let me make sure I got a good marker for this for when I get to that point. Let's do green. So electrons are found in the energy levels, and as you move down the periodic table, the elements are going to have more electrons, and therefore their electrons are going to be organized into more energy levels in order to keep them revolving around the nucleus. Now, because energy levels are where we find electrons, they're all going to be negatively charged areas. Now, we just said that the nucleus being positive is pulling in on the electrons, but all of that pull in is also fighting with the fact that there's other electrons in the way. And so if we're talking about a positive-negative attractive force, if I put something between those that's either positive or negative, it's going to interfere with that interaction. And so what we see with the idea of shielding is that as you move further out, the more energy levels you have, the more you're going to see shielding occur. And what shielding is basically as the electrons from the outermost level are being pulled in, we're actually going to see the negative impact. Hold on. Okay. So in green, I've kind of drawn the shielding force. So the nuclear charge is what we have here in the reddish pink. And so that's the more positive the nucleus is, the more it's going to pull in on its electrons. But those electrons are, while they're trying to pull in, while their energy is trying to, their charge is trying to attract to the nucleus, the electrons that are kind of in between them and the nucleus are going to be pushing out on them, because positive and negative things attract to each other. Negative, negative repel, positive, positive repel. So what we see there is that even though the electrons in the further out energy levels are being attracted to the nucleus, they're being attracted less and less, not just because of their distance, but also because of this repulsion between the electrons in the lower energy levels. So the electrons that are in the lower energy levels are repelling the outer energy levels, and so even though they're pulling into the nucleus, yes, there's still some kind of push back out. So as you move across a row on the periodic table, shielding stays constant. The question is why? So in your notes, you're going to want to answer that, to say, as you move across a row on a periodic table, shielding stays constant because a row of the periodic table is representative of the electrons fitting into an energy level of an atom. So when we move across a row on the periodic table, we're adding electrons to the same energy level. We're not adding any more energy levels. Therefore, we're not adding any more interactive levels of repulsion. And so as you move across the periodic table, it's going to stay constant. As we move down the periodic table, we see that shielding is going to go up, because using the periodic table as a tool for electron configuration, we see that as we move down the periodic table, the different rows of the periodic table are representative of the energy levels that electrons can fit in. So the further you are down on the periodic table, the more energy levels you have. Therefore, the more shielding you're going to see. Now, nuclear charge and shielding kind of fight with each other, because the blue in this image right here is the nuclear charge attraction, the attraction of those electrons pulling in. But the shielding problem, or the shielding force, are the red bars, the repulsion that occurs between energy levels. So each energy level that we add on is going to decrease the nuclear charge. And so every time we add an energy level, we're going to see that not only are the electrons in the further out energy levels just further away from the nucleus, but we're increasing the repulsion between the energy levels. And so the actual nuclear charge, or the actual force of attraction on the outermost electrons, is less than what we expect it to be based on the size of the nucleus, because of the fact that we're adding more and more energy levels. This is referred to as the effective nuclear charge, also sometimes referred to as ZEF. Now, we're going to talk about effective nuclear charge. If you go on to more advanced courses, you'll dive deeper into it and you'll calculate effective nuclear charge. But what we're basically saying is, if we have the overall attractive force of the nucleus minus the repulsion of the energy levels below the outermost, that's our ZEF. So essentially, in this image, ZEF is the blue minus the red. And so when we're talking about effective nuclear charge, that's what we're saying. What is actually happening? Now, because of the fact that with more energy levels, we have more... Because of the fact that with more energy levels... Sorry, I had a glitch on my computer. Because of the fact that we have, with more energy levels, we have more shielding, the nucleus is not able to hold on to those outermost electrons as easily. And so what we see is that they kind of spread out a little bit more. If I can't hold on to them, they're going to spread out a little bit more. So the stronger the effective nuclear charge in an atom, the more it's tightly holding on to its electrons. And if we recall back to Unit 1 or Unit 2, we said that the size of an atom is based on essentially the size of the electron cloud, how big the electrons are, or how spread out the electrons are compared to the size of the nucleus, or the size of the atom itself. So if the nucleus is holding on to its electrons very tightly, it's going to be pulling them in very tight, and that's going to affect the overall size of the atom, or the radius of the atom. We're using the term radius because most atoms in general are spherical shaped, and so we're talking about the radius of it. So as you move across a period of the periodic table, so as I go from lithium to beryllium to boron, carbon, etc., what we see is a decrease in the size of the atom. Because think about what's happening here. If I'm moving across a row, I'm not adding any more energy levels, so shielding isn't going to be going up, but I'm adding more protons. Each time I move from carbon to nitrogen to oxygen to fluorine, I'm adding a proton each time. And so I'm increasing the positivity of the nucleus without affecting the nucleus's ability to pull on its outermost electrons. So as we move left to right across the periodic table, we see that the atoms get smaller and smaller because more positivity in the nucleus and no change in the kind of interference. As we move down a group, though, atomic radii, even though going from lithium to sodium, I go from element 3 to 11, I'm adding a lot more electrons, or excuse me, a lot more protons in that case, but I'm also adding another energy level because I've had to add more electrons. And since I've added another energy level, I've added more interference. So even though as I move down from lithium to sodium to potassium to rubidium to cesium to francium, etc., even though I'm increasing the number of protons, I'm simultaneously increasing the interference that there's going to be between those protons and the electrons of the atom. So what we end up with is a situation where the atom radius gets bigger as I go down the periodic table. So the largest atom on the periodic table is francium in the bottom left corner of the periodic table. Now, when we create cations and anions, we're adding and subtracting electrons. So when an atom is going to create a cation, we're losing electrons. Now, if I'm losing the electrons in my outermost energy level, I'm essentially getting rid of that energy level. Now, what that means is that it's going to be a smaller ion. If I have an atom and I lose an energy level, then the atom's going to be smaller. So cations are always going to be smaller than the atom that they came from. Anions, if I have an element that's going to create an anion and then I add electrons to it, well, electrons are negative, they're going to repel, and either I'm going to be adding an entire new energy level, or I'm going to be just adding more electrons into the current energy level, which causes them to start to expand and spread out. So cations are always going to be smaller than the atom that they came from because they're losing energy levels. Anions are going to be larger because they're either gaining energy levels or the electrons in their outermost energy level are repelling. Now, that relates to the reactivity of elements as well. So reactivity is essentially how likely they are to try to shift to that 8 valence electrons. How much do they want it? So elements that form cations are going to be mostly metals. We saw that in our notes in class today. Metals want to lose electrons. Therefore, more reactive metals can more easily lose electrons. So let's think about that. Metals that are the most reactive are the metals that don't have a very good hold on their electrons. Their electrons can easily be lost. So when we think back, the most reactive metals are going to be metals that are very close to their goal. So the metals that only have 1 or 2 valence electrons, they're going to be the ones with the lowest nuclear charge because there's going to be less pull in, and the ones that have more shielding. So the more shielding we add, the less the nucleus can hold on to the electrons. So by the time you get to an element like francium, it can barely even hold on to its electrons at all. And so those electrons are ready to be lost. That makes it extremely reactive. Now on the anion side, elements that are nonmetals are attempting to form anions. They want to gain electrons. Therefore, if I'm a nonmetal, the most reactive nonmetals are going to be the ones that can most easily gain electrons, meaning the ones that can most easily pull in electrons. That's going to be the ones that have the strongest effective nuclear charge. So the more reactive nonmetals are the ones that have the highest nuclear charge with the least amount of shielding, meaning they have the highest effective nuclear charge. So that's going to be kind of the top right corner of the periodic table. The elements that have, the nonmetals that have a large nuclear charge compared to the others, and the ones that have the least amount of energy levels, the least amount of shielding. So when I have a very positive nucleus and I don't have a lot of shielding, then I'm going to be able to easily not only hold on to my current electrons and keep them tight, which is why they have small atomic radii, but also that positivity is going to stretch beyond the atom, and I'm easily going to be able to pull in more electrons. So the most reactive nonmetal then is fluorine. Chlorine, yes, has bigger nuclear charge than fluorine. It's right below it, but because it's below it, that also means it has another energy level. So it has a little bit more shielding. And so as a result, that reduces its ability to pull in new electrons beyond the atom. So metals want to lose electrons, so the most reactive metals have a very low positive charge and a lot of interference, making it very easy for those electrons to just fly off. Nonmetals want to gain electrons, and so because they're trying to gain electrons, the stronger the charge of the nucleus and the least amount of interference, the better. All right, so that's a lot of information. What you're going to do now is go ahead and start working through your practice worksheet, and then we're going to use that to kind of review and go over in our next class. Next class, we're also preparing to do a lab, so be ready for that. See you then. Bye.